everybody. So in this short video, I'm going to talk about the idea of conservation of angular momentum. So we've already seen how to calculate angular momentum for an object or a system where you say have, an airplane flying over a point on the ground. So even though it has linear momentum, there's still angular momentum for that system. And so now we're going to see how that comes together into a really fundamental law, which is conservation of angular momentum. So just like conservation of linear momentum, this will be for immediately before and after some event. So the sum of all initial angular momentums, which is capital L, of a system is going to be equal to the sum of all final angular momentums, again, capital L. And remember that L can be calculated from R cross P, for example, the airplane, or from I omega for something that's already has some rotation. So whichever one you find most convenient. And importantly, in terms of problem solving, this applies immediately before or after. And in this case, it's not always a collision. I'm just going to say some sort of event. So before or after some sort of event. And that's going to be, again, very key in problem solving. So it doesn't apply. There has to be no external torques. So no significant external torques. Really, we want no external impulses, right, which has to do with the force and time, or the torque and time. And so we don't want any substantial external torques acting on our system. So if I have this rod and it's hanging at rest in its horizontal position, and then I pivot it and it swings downwards, angular momentum is not conserved, right? It started off at 0 and it ends up as not 0. So that's not conservation of angular momentum. And the reason is that there's external torques acting on this system. So instead, conservation of angular momentum will apply, for example, with an ice skater spinning on the ice, and we're going to ignore any friction from the ice. And then she's able or he's able to move their hands in. And what they're doing, the event in this case, is changing the angular momentum of the system. So they're able to lower changing their moment of inertia of the system, not the angular momentum. They're able to lower their moment of inertia, right? So that's the event, lowering their moment of inertia by bringing their mass close to their body. And by lowering your moment of inertia, then if angular momentum is a constant, because there's no external torques, everything's internal to the system, then what's going to happen, because L equals I omega, if I goes down, omega will go up, and the ice skater spins much more quickly. So that's an example of an event. So types of events to be on the lookout for is a change in the moment of inertia of an object or of the system. So a change in moment of inertia. So then the angular momentum before the change in moment of inertia is the same as the angular momentum after. Another event would be some sort of collision that results in rotation or some sort of rotation that results in linear motion. So let me explain what I mean by both of these. So first, let's say I have this bar and it's just hanging vertically in a field or in a gravitational field. And then I have a mass that's going to come straight line, right? And this is pivoted up here. The straight line mass comes, sticks to the object, and the object's going to then swing upward, right? So that's a straight line motion, a collision that resulted in rotation. So the angular momentum of that system is conserved, and that's how you analyze that system. Now, remember that this straight line motion does have angular momentum relative to the pivot point. So the initial angular momentum here, the R cross P, right before it hits, the instant right before it hits, equals the angular momentum right after of the object and the rotation. So that's an example. Another example would be that in reverse. Let's say that I have an object here and then I swing this down. So it starts from rest, say it swings down, it hits the object, and the object then goes off in linear motion. So that sort of collision The collision that either works as linear motion causes rotation, or rotation causes some sort of linear motion, those also apply for conservation of angular momentum. But the idea is that there has to be some sort of event, a change in a moment of inertia, or some sort of collision. Something falling or changing its height will not be conservation of angular momentum. So you're just going to basically add up all initial angular momentums, and that's going to be relative to some pivot point. And then you're going to set that equal to the total final angular momentum relative to that same pivot. Right? So if this is the case of something coming in and it strikes the rod and then it moves upward, this is the pivot point where the rod is pivoted, because that's where the final angular momentum, you're going to calculate it relative to that. So you have to be consistent with the pivot point before and after. All right, so there are quite a few examples for you to learn from, and that concludes the introduction to conservation of angular momentum. As always, let me know if you have any questions.